Hi nerds, it's really important that you subscribe. So go ahead and do that now. Now please. Alright, thanks for doing that. Let's continue looking at the PIC16F684 block diagram. Let's take a look at the ALU. The Arithmetic Logic Unit, ALU, in the PIC16F684 microcontroller is a critical component responsible for executing arithmetic and logic operations. Here's a detailed overview of the ALU in the context of the PIC16F684 block diagram. Arithmetic operations. Addition, subtraction. The ALU can perform addition and subtraction, which are fundamental operations for data manipulation and mathematical computations. Increment, decrement. The ALU can increment or decrement values, which is often used in loops and iterative processes. Logic operations. And, or, XOR, not. The ALU can perform bitwise logical operations such as AND, OR, XOR, and NOT. These operations are essential for tasks like masking, toggling bits, and implementing logical decisions. Shift operations. Left-right shifts. The ALU supports shift operations, which are used in tasks such as bit manipulation, multiplication, and division by powers of 2. Status flags. The ALU affects various status flags in the status register, which include 0 flag, Z, which is set if the result of an operation is 0. Carry flag, C. This is set if there is a carry out from the most significant bit in addition or a borrow in a subtraction. Digit carry flag, DC. This is set if there is a carry from the 4th bit, and this is used in BCD arithmetic, binary coded decimal. Power down, PD, indicates if the device is in sleep mode. Timeout, TO, indicates if a watchdog timer WDT timeout has occurred. Interaction with the W register. So we're talking about the ALU and its interaction with the W register. The ALU typically interacts with the working register, WREGE, which is a general purpose register used as an operand in many instructions. Operand sources. Operands for the ALU operations can come from various sources such as the WREGE, file registers, general purpose and special function registers, and immediate values encoded in the instruction. As a heading, result destination. The result of an ALU operation can be directed to either the WREGE or a file register, depending on the specific instruction being executed. So we're still talking about the ALU. Integration with the control unit. The ALU is tightly integrated with the control unit, which decodes instructions and controls the operation of the ALU accordingly. In the block diagram of the PIC16F684, the ALU is a central component connected to the data bus, facilitating the transfer of data between various registers and the ALU itself. It works in conjunction with the program counter, the instruction register, and the control unit to execute instructions stored in the program memory. The efficient functioning of the ALU is crucial for the overall performance and capability of the microcontroller. Next, let's talk about the multiplexer, MUX, that is in close proximity to the ALU. In the PIC16F684 microcontroller, the multiplexer, MUX, connected to the ALU is an important component that selects the appropriate input for the ALU operations. Here is a detailed overview of the MUX in the context of the PIC16F684 block diagram. MUX connected to the ALU. Its function. The MUX multiplexer is used to select one of several input sources and direct it to the ALU for processing. This allows the ALU to perform operations on different sets of data as required by the current instruction. Inputs to the MUX. The MUX can select inputs from multiple sources, typically including WREGE, W register, the working register, which holds one of the operands for the ALU, file registers. So again, this is on the topic of the MUX can select inputs from multiple sources, typically including, and then it has W register, file registers, immediate data, literal constants, control signals. So now I'm going to talk about file registers as one of the inputs that the MUX can select. File registers, general purpose or special function registers, which can contain data or control information. Next, as one of the things the MUX can select as inputs from multiple sources, immediate data, constant values provided directly in the instruction. Next, literal constants, values defined in the program code. Control signals. So this is all under the category of the MUX can select inputs from multiple sources, typically including control signals. The selection of the input source by the MUX is controlled by the control unit of the microcontroller. The control signals are derived from the decoded instructions, ensuring that the correct operand is selected for each ALU operation. Operational context. During the execution of an instruction, the control unit determines the required operation and configures the MUX to route the appropriate operand to the ALU. For instance, if an addition operation is to be performed, the MUX will select the operands specified by the instruction and pass them to the ALU. Data flow. The selected input is passed through the MUX to the ALU. The ALU then performs the desired arithmetic or logic operation on the inputs and produces the result, which is then stored in the appropriate destination register, such as WREGE or a file register. Integration with ALU. The MUX is tightly integrated with the ALU, forming a critical part of the data path within the microcontroller. This integration allows for flexible and efficient processing of various types of data and instructions. Block diagram representation. In the block diagram of the PIC16F684, the MUX is typically shown as a switch or a set of gates that can connect one of several inputs to the ALU input. The control signals for the MUX are derived from the instruction decode logic. In summary, the MUX connected to the ALU in the PIC16F684 microcontroller plays a crucial role in selecting the appropriate input source for ALU operations. By routing data from various sources such as the WREGE, file registers, immediate values, and literal constants, the MUX enables the ALU to perform a wide range of arithmetic and logic operations as dictated by the program instructions. The control unit orchestrates the selection process, ensuring that the correct data is processed by the ALU at each step of the instruction execution cycle. Next, I would like to talk about the WREGE. This arguably is something I should have covered first. Only now am I getting to discussing it. In the PIC16F684 microcontroller, the working register, rather WREGE, plays a crucial role in the microcontroller's operation. Here's a detailed overview of the WREGE in the context of the PIC16F684 block diagram. WREGE, working register. Function. The WREGE is a general-purpose register used to hold one of the operands for arithmetic and logic operations performed by the ALU, Arithmetic Logic Unit. It acts as an intermediary for data transfer between the ALU and other parts of the microcontroller, such as file registers and memory. Role in operations. Most instructions that perform arithmetic or logic operations use the WREGE as one of the operands. For example, in addition operation, one operand is typically in the WREGE and the other operand can be in a file, register, or an immediate value. The result of an ALU operation can be stored back in the WREGE or in another specified file register. Instruction interaction. Many instructions explicitly use the WREGE, such as move WF, which means move WREGE to a file register, and move F, MOVF, move file register to WREGE. Instructions that manipulate data, such as add WF, add WREGE and file register, sub WF, subtract WREGE from file register, and logical operations like AND WF and WREGE with file register involve the WREGE. Integration in the block diagram. In the block diagram of the PIC16F684, the WREGE is typically shown as a central register connected to the data bus. It interfaces with the ALU, allowing the ALU to fetch one operand directly from the WREGE. It also interacts with the MUX, multiplexer, which selects inputs for the ALU operations. The WREGE can receive data from the ALU after processing, or it can be loaded with data from other registers or immediate values through the data bus. Data transfer. The WREGE is involved in transferring data between the microcontroller's CPU and its memory or I/O ports. For instance, data read from memory or an I/O port might be placed into the WREGE before further processing or storage. Special instructions. Some instructions are designed to work specifically with the WREGE without involving other registers. For example, clear W clears the WREGE, setting it to 0. Summary. The WREGE in the PIC16F684 microcontroller is a versatile and essential register used extensively in arithmetic, logical, and data transfer operations. It serves as a primary operand source and destination for the ALU, facilitating efficient data manipulation and processing within the microcontroller. The WREGE's integration in the block diagram highlights its central role in executing instructions and performing various operations that are fundamental to the microcontroller's functionality. Thanks for listening, and stay tuned for my next video, and please subscribe if you haven't done so already. Thanks for watching. Bye.